Something like that. Right, good morning everybody. So, I prefer that one. So this is why we're all here, right? Everybody wants a flexible OLED TV that's wallpaper and whatever, right? And it's our job to make the materials that go inside. So, a nice simple task, right? So what I want to do in this first 45 minutes is go through some of the basic photophysics that we use to help to understand how the molecules are starting to work in terms of how TADF works. That directly fed into the work with Tom, and I've lost him somewhere. Where is he? Oh, he's over there today. I won't put the laser on you. Right? So I'll show you how the kind of measurements that we took led to building up that theory of second order vibronic coupling. And then from that we'll look at some of the more simple ramifications of that model and how we can then see in the experiment how that model starts to be predictive. And then in the second lecture I'll take it further forward and show you some of the new things that we're doing in terms of understanding these TADF molecules in more detail, which will hopefully help the chemists more than anybody else. Okay? So some of you, especially the Exelite people and people that I've visited, have seen a lot of these slides before, but we'll just go through and point out the highlights. So I'm going to try and go on this side more today, because I notice that everybody's right-handed immediately does this. This is more difficult, so you guys, I'm going to try and treat you guys over here. Right, so you've all seen this picture, right? Chihiro Adashi's original idea of how TADF worked. What that's based on is the original work on eosine dye. My paper was Parker in 1964, but you put 1961, didn't you? All right. Anyway, Parker was working in England looking at these eosine dyes, and he realized that you had this thermally activated delayed fluorescence component. They'd only just realized that you got a singlet and triplet state, and they were separate states. And at the time, they were just trying to understand what a triplet was, and they'd found this thermally activated crossing. Right? So Chihiro was looking at this to try and obviously use a way to harvest triplets in the device, and he just basically copied Parker's diagram, this basic idea. What he didn't say, in a way lucky for him, but what he really meant was he thought you'd got a real singlet and a real triplet, and he thought this was the CT singlet and this is the CT triplet. Okay? And the idea being that when you get a good CT material, you can close this gap. Right? And there's lots of evidence in the literature. So if you go and look at these papers by Beans and Fredericks and people like that, you'll see that all the work on CT states and understanding what CT states is out there in the literature, and you can find it. Okay? And just to annoy Chihiro even more, TADF was actually christened first in 1968 in a book chapter by Wilkinson and Horrocks. Right? So even TADF isn't new. The name had been out there since 1968. So let's have a look at some of the basics that we understand about TADF and where the theory of second order vibronic coupling comes from. So the obvious thing is, and the obvious thing we did first, and this was done in Durham, was just to do simple, she's over there, so I've got to remember, very, very simple DFT. Right? Just to look at, I'm an experimentalist, remember, so we just took this basic compound and we called it 2D, and if you look in the first paper by Fernando that's got the whole family of different compounds where we basically did molecular Lego. So we had a few acceptors and a few donors, and we put A with B, B with C, C with D, and we just made this whole template of different materials. And we gave them really, really good names. 2D, right? So being physicists, we can remember what 2D is. Don't ask me what the real chemical name is. It's this long. So, and so we just did the DFT, and we looked at it, and we looked as a function of that angle, changing the torsion angle between the donor acceptor. And yes, lo and behold, when you get to 90 degrees, it looks like the singlet and triplet gap disappears. So that's the gap between the lowest singlet state and the lowest triplet state. And I'm not telling you anything about the singlet state and the triplet state. Okay? So yes, that's obviously it works. And so that's why we started to hunt for these DAD molecules where we could either get them to go 90 degrees or we might be lucky and they would go 90 degrees. So that's the rationale of what we did. And we came up with, in the second generation of materials, 2K. Right, there's its real name, if you want it. 2K is our favorite molecule. And the good thing about 2K is when we did the crystal structure, it gives you orthogonal donor acceptors straight off. Nature does it all for you. We were very, very happy. And all it is because it's the donor and the acceptor are bound through the nitrogen. So effectively, you bond through the nitrogen, you end up with orthogonal donors and acceptors. And we thought, this is it, gold dust, this is fantastic. We can retire to the Bahamas, we're made. Okay? So then we started to try and understand this molecule and pick out the useful things. So I want to show you the spectroscopy, how we pick out the useful things. So how do you read the spectrum? What's the important bits? So yes, you can do DFT, and you can get, you can look at where the HOMO and the LUMO are, and you look and say, yes, that looks like a fantastic charge transfer state. And in fact, they're quite good, these molecules. You get something like 98% of the ground state is in the HOMO and 97% is in the LUMO. There's a real HOMO-LUMO transition with almost pure charge transfer characteristic. And you can do the molecular modeling, and the molecular modeling says, yes, it's orthogonal donor and acceptor. And you can even see that the acceptor is slightly bent because it's phenothiazine. Right, we're going to spend a whole 45 minutes talking about that after second lecture. So off we went. Well, not me, off went Fernando. He's sitting there. So most of the spectroscopy, the original spectroscopy, was done by Fernando. And then it's done by the rest of the group after that. So Fernando loves these spectra now, but we've seen them so often that... So the key thing is, and this is how we do the spectroscopic characterization. We have the molecule 2K, but we also look at the donor fraction and the acceptor fraction on their own. And we do the comparison of the donor unit, the acceptor unit, and the CT molecule, the donor acceptor molecule. And in that way you can start to tell a lot more. When we start to look at the triplet properties, it's the only way you can understand what's happening with these molecules. Okay? So the key point on this absorption and emission spectrum is, if you look down here, right on the foot of the absorption spectrum, okay? I don't like these two boards, it's going to be difficult. But you can see that the black is the absorption of 2K, the blue is the acceptor unit on its own, the red is the donor unit on its own, and the absorption of 2K is just a simple summation of the donor and acceptor. So it basically looks like the molecule doesn't care that the donor acceptors bound together. You've got an acceptor unit and a donor unit, they don't talk to each other, they just happen to be bonded together. Right? Tells you they're orthogonal. They're not coupled in the ground state, which is what the X-ray says, what the modeling says. We've got what it says on the tin. We've got an orthogonal donor acceptor molecule. If you look at the emission of the acceptor and the donor, you can see you've got well-resolved acceptor and donor emission, but when you look at the emission of 2K, then you get a completely new band, completely redshifted with respect to the donor and the acceptor. Everybody says, oh look, it's almost Gaussian, it's a charge transfer band. Right? Well, yes it is, and it shows you that you really do have strong charge transfer. The structure on there, whether the structure on there is important or not, we can talk about later on, right, what it means. But at the moment, just doing this simple first run of doing the characterization of this molecule, you can see a lot. The donor acceptors aren't coupled in the ground state, but in the excited state they are, and you get a CT. The really good thing about this molecule is that that spectra was done in MCH. The MCH is about as non-polar as you can get. The molecule still gives you a really good, strong CT state without stabilization of the solvent. And that's critical so that we can do lots and lots of different spectroscopic measurements on this system. So what's not happening here is like a ticked state where you excite it and then you get some kind of geometric reorganization of the donor acceptor to stabilize the CT state. I'll show you other systems where you can see the stabilization, but the important thing for us was that we can then put this into inert materials and still have it in the CT state. So it allows us to do spectroscopy much more easily. The materials that had carbazole as the donor don't do this, because in the carbazole you don't have this orthogonality so strongly. You need to stabilize it with polarity with a carbazole. So carbazoles are harder to look at. Okay? So this tells you a lot, just this simple emission and absorption straight off. Okay? But of course for us the key thing was we wanted to know where the triplet states were. Right? And then we wanted to try and find out what the triplet was. So this is the phosphorescence spectrum in pink down here. And this is just looking at the time-resolved emission from about a microsecond, which is the CT emission, down to 80 milliseconds, which is this well-structured vibronic phosphorescence. Okay. So straight away you can see the phosphorescence is different than the CT emission. So this is why we say that this is the phosphorescence from local triplets. The local triplets being the triplet state of either the donor or the acceptor, which aren't coupled. Okay. So to start with, we looked at this, and of course we took the onset of the phosphorescence, and we got the energy of about 2.61 eV, and we would say that the triplet state, wherever the triplet state is, and I'm not saying what it is, was actually higher energy than the CT state. So the time when we first thought that for TADF, the TADF was between the CT singlet and the CT triplet, we thought this was good because the local triplets were out of the way of the CT states. So we thought CT states are below the local triplet won't quench the CT triplet. Absolutely fantastic. But, you know there's a but. I'll come to the but in a second. So the second simple thing you can do, right, which is what Fernando, in his well-trained wisdom, it's triplet state, so if we bubble it with oxygen, it goes away. Well, yes, it does. And in this particular molecule, if you look at the emission with and without oxygen, you get something like a factor of 12.5 difference. So something like 90% of all the fluorescence comes from something that was triplet at some point in its lifetime. And the oxygen quenches it. So we look at this and go, this is TADF, this is fantastic. You've got something, 90% of all the things that emit had triplet character. So we must be harvesting all these triplets. And the quantum yield of fluorescence, the total emission in air is 3%, and in oxygen-free solution it's 33%. So it looks like you've got a 91% triplet yield. So that's basically what that measurement's telling you. Okay. You can then step away a little bit from optical measurements, okay, and you do electrochemistry. And who did the electrochemistry on this? It was before data, I think. You did that. There he goes. I did that, he says. Yeah. Yeah, this is true. Yeah, you've been there a long time already. Right, the key thing about the electrochemistry is, yes, you know that it can tell you where the effective electron affinity and ionization potential are. Okay? But again, what we did was we compared the donor unit, the acceptor unit, to the molecule to get more information. And what you can see is the molecule, the 2K molecule being in black, looks almost identical to the oxidation of the acceptor, and there's a little difference between the reduction of the donor, but basically The electrochemistry says you've got a donor and an acceptor, and you can oxidize and reduce them, and they don't care that they're bound together. So again, the donor acceptor unit are orthogonal. They don't talk to each other in the ground state. So at the time we just thought, oh, that's fine. That, it fits everything we can understand. So we're starting to build up a picture of what these molecules do. I'll come back to this in a bit about how we can use that to understand other things. Then we turned over to doing time-resolved measurements, to see what was happening as a function of time. So I just put this up to remind Fernando that once upon a time he actually worked in the lab. That's Fernando working one afternoon when I snuck in and took a photograph. Okay. So as I go through, I'll explain how we do these ICCD measurements. But basically, the first thing we did was because it's a CCD, you can get a whole spectrum. And you get a spectrum as a function of time. So the most useful thing to understand is just looking at what emission species you have over the whole decay of the emission. So you can see here, at very early times, like a nanosecond, you can actually see the emission of the donor. Right? So what we're actually doing, when we excite the molecule, we excite into the donor. So we hit it with 355 nanometers from a YAG laser, you excite the donor. And you can see that the donor is actually emitting. It decays in about 5 nanoseconds, 6 nanoseconds, and it decays and you see the formation of this CT emission. So in this molecule, you can resolve the electron transfer step. And in fact, the electron transfer step is incredibly slow. That's because your donor acceptor are orthogonal when they don't talk to each other. It's just a simple effect of the molecule. But you can see it. Okay? You can then see for a long period of time, from nanoseconds well into the microseconds, you get this CT emission. You get a little bit of relaxation. So the CT energy is shifting slowly with time. Okay? And then for almost into the millisecond, you see CT emission. And then right at the very end of the measurements, into the millisecond, you start to see the phosphorescence again on its own. And this is the phosphorescence. Right? So the phosphorescence spectrum on here is actually the dimer molecule, the DA on its own, because we got that one resolved first. What we did was that we realized that when we do this measurement, if we concentrate on the phosphorescence, we could time resolve and get a much better phosphorescence spectrum out of it. And what we suddenly realized was, by doing the phosphorescence of the donor, phosphorescence of the acceptor, phosphorescence of the 2K molecule, we could actually resolve the phosphorescence of the 2K into a contribution of the acceptor phosphorescence with a contribution of the donor phosphorescence. So in that molecule, you're getting dual phosphorescence from the local triplet of the donor and the acceptor. So you know that those localized excited states of the donor acceptor still exist on the 2K molecule. Right? The 2K molecule can give you a CT excited state, but you can also have the excited states of the donor and acceptor living in harmony with it, if you like. Okay? So now that we can actually resolve the phosphorescence, we can find that the actual lowest energy triplet state is coming from the donor. Right? And it's at lower energy than if we just took the onset of the normal phosphorescence. So now we realized that the lowest energy triplet was about 100 millielectron volts lower than we thought from just simply measuring the phosphorescence. So the lesson that we learned was A, resolve the phosphorescence as best as we could, and by comparing it again to the donor acceptor, we can actually find out what the lowest energy triplet of the system is. Right? So normally 100 millielectron volts, we would just say, that's nothing. In these materials, 100 millielectron volts is enormous. And what we really learned was we had to recalibrate our energy scale. So before, 0.1 eV was kind of, it's nothing, it's in the noise, we didn't care about it. Because everything we were looking at was 3 electron volts, 2.5 electron volts. Now I'm going to start talking about systems where 5 milli-electron volts is important. So you can see that that energy difference is huge and it matters. And it really matters. So when you want to, you've got a new molecule and you want to find out where the lowest triplet is, you've got to do it carefully and you've got to really resolve the phosphorescence to find out where the lowest triplet of the state is. It's important because these energy scales now are much smaller than before. So I'm going to have to hurry up a bit. The other thing we can do with the CCD is, of course, we can just measure the total intensity as a function of time. And the great thing with the CCD is you can do it for 8, 10 orders of magnitude in time. Right? And because of the sensitivity and the way you can run the CCD camera, you can quite easily measure 10 decades of intensity in one experiment. So you just sit there, you keep firing the YAG laser, you let the camera look at later and later and later times, you integrate each time, you get the spectrum, and you can then get the total intensity. So not only are those points total intensity, there's a spectrum behind each of those points as well. And if you look at the spectrum, you can see that almost all the time, the emission, all the way down this, what we call the prompt CT emission, and then the delayed CT emission, is always exactly the same emission. It's always coming from the same species. So this prompt part and this delayed part. When you put the oxygen in, the delayed part is the part that goes. Now remember, for this molecule we said that something like 90% of the emission came from effectively the delayed component, because it come from the part that was triplet. And you look at this and you think, but the prompt part here is much bigger, much more intense than the delayed. That's because this is logarithmic time. And you have to realize that all our plots on here are log of time. So the area under that delayed part is much bigger than the area under the prompt part. So when we take the ratio, so we measure the ratio of the area under the prompt and the area under the delayed, we get a ratio for this particular molecule, 2K, of about 10. It's 10 times more delayed emission than prompt emission. And so that tells us again that that's in fantastic agreement with the fact that you put oxygen in and you get a triplet yield of 90%. So it's self-consistent. So the lifetime of the prompt CT emission is around 15 nanoseconds. The lifetime of the delayed component is 5 microseconds. It's much longer. Okay? And only right at the very end of the millisecond do you see a little bit of the triplet left. So almost all of the triplets are being harvested by DF, but there are a few left that you can measure to get phosphorescence. Right? And that's how we fully characterize the emission process of these TADF molecules. And then just to prove that it's TADF and not triplet annihilation.
I have a question.
Yeah.
In the slide before, the fluorescence and the phosphorescence, what is the energy in a spectrum?
Yes, I'll show you on some other examples where the prompt CT relaxes, but the DF usually doesn't. Usually you get relaxation down here and then it stabilizes.
Then practically they don't perfectly overlap, right?
Well, the shift is only something like 30 to 40 milli-electron volts. So on this kind of scale, you can't see it, but it is there. All right, but there's more examples that show it much better. Okay. So the other thing you need to do is, the oxygen experiment is, English term, very rough and ready. It tells you that there is a component there that was triplet. It really, the ratio between emission with and without oxygen depends on the lifetime of the delayed fluorescence and the diffusion rate of oxygen. So there are some materials which are fantastic TADF and the oxygen doesn't touch it. I should have got an example somewhere. So of course what we do is we look at the delayed component of the emission, and we measure the intensity dependence of the delayed fluorescence component. So this is just by ramping up the pump laser. And in all these cases, we always see a completely linear dependence of the delayed component on the pump laser intensity. Right, so it's one photon in, one delayed photon out. If it was triplet annihilation, it would be 2 photons in to generate 2 triplets, which would annihilate to give you 1 photon out. So that's why it's quadratic. And we'll talk about that in the 3rd lecture. So this is, if people say they've got TADF in a molecule, you've got to show me this. If you don't show me you've got a linear power dependence on it, I won't believe you. There can be too many other things. This is one of the real key signatures of TADF. Okay. So I said the nice thing about the 2K molecule was the fact that it's strongly CT in a completely non-polar environment. So we could put the 2K molecule into ZNX. Right? You've seen ZNX mentioned a few times already. ZNX is the clear branched polyolefin polymer you make compact discs out of. It's a fantastic host. It doesn't crystallize. It's completely amorphous. That's why they use it for compact discs. And it's readily soluble, so it's easy to get these molecules in. So it's an ideal host, but it's non-polar. So if you've got a TADF molecule that doesn't give you the CT state in non-polar environment, you can't do these measurements. This is why 2K was very good for us, because it does give you CT in non-polar. So you put it into ZNX, you can see exactly the same kind of behavior. You get the decay of the prompt emission at early times. Right? And you can even resolve the emission of the donor quite well. You see the prompt decay, and then you get the delayed component. Right? And on here you can see that the prompt component is temperature independent, and it's only the delayed fluorescence here which is temperature dependent, which is as it should be. Right? It's only the contribution from the TADF which is thermally activated. So it's the delayed component which is thermally activated. The prompt is just normal emission from the CT. Right down the end we get a bit of phosphorescence, and it's the donor phosphorescence. See down here. Right? And on here we've put what happens to the actual wavelength. So first off, we start up here. We're getting emission from the donor, so it's way up in the blue. You suddenly lose all that donor emission, and you get prompt CT. And then over time, when you look at the spectra carefully, it blue shifts. And the reason that the delayed component blue shift is nothing to do with the CT state. It's just that as the CT state gets weaker and weaker and weaker, the phosphorescence, which is slightly bluer, gets comparable to the delayed emission, and the actual emission spectrum shifts to the blue because you get the component of the phosphorescence making it look like it's blue shifting. So the CT doesn't shift, but the spectrum does because of the triplet component. Yeah? That's in the delayed, but that's not what happens at early times, and I'll show you later on. Right? So you can see immediately, you can understand now how these molecules are working, which part of the emission is temperature dependent, which is thermally activated, which is not thermally activated. You've got different components. You're still getting a little bit of phosphorescence, so you're not getting complete harvesting. You can do that in ZNX. You can do it in CBP. So you can take it a bit further to do a measurement which looks a bit more like in a device. And in fact, this was done in CBP, and we concentrated on that really early time, so the first 5 nanoseconds. And you can see if you compare this emission to that of the donor, you can see that this first really early component is the donor emission, and as the donor emission is quenched, you get the onset of the CT. So we know we're getting electron transfer, the electron transfer from the donor to the acceptor to form the CT state. But the rate at which you get the electron transfer is about 10 to the 8 per second. Something like 4 orders of magnitude slower than a normal electron transfer in a normal CT. I think that we're proud to say we have the slowest electron transfer ever reported. Yeah? And it's just a simple fact that the donor acceptor are not coupled. And it tells you the electron transfer process is going via the coupling of the orbitals, and it's behaving just like everything else. Okay? So you can understand a little bit about this basic electron transfer. I'm not going to say too much about it, apart from it's really good and slow, and we can actually do measurements on it. Okay? Right. So then we took 2K molecule and we put it into a device, and it works fantastically well. Right? You get devices that, when you just get a few photons, 10 candela per meter squared, it's a few photons, you can measure them. The EQE is 20%. So that's just the 2K molecule in a really, really simple 3-layer device. Okay? So if you look at the characteristics, you get a nice turn-on voltage. The turn-on voltage is very low. For a 3-layer device, the turn-on voltage is amazingly low. Even Carsten's got to admit that 3 volts for a 3-layer device isn't bad. And the roll-off is not too bad up to about 1,000 nits. Then it gets killed very quickly. So the good thing is, again, because that 2K molecule forms a CT state in non-polar environment, you can put it into a normal host for a device like CBP or whatever, and it works. So again, we were fortunate to have this molecule because it allowed us to see all these things first off. But said we get this fantastic efficiency, and we said yes. Well, we must be harvesting all the triplets in a device, because if we look at the equation for EQE of an OLED, and we assume outcoupling of 30%, we were being generous. We do the calculation. We're saying we're harvesting 100% of the triplets, no problem. The PLQY of the emitter was 30% oxygen free. That's great. So we put the numbers in. EQE should be 9%. If the PLQY of the emitter is only 30%, everything else is maximized, you get 9% EQE. But we're getting twice that. We were getting nearly 19% EQE. So that said that the actual PLQY of the emitter was effectively 65%. So where did this extra twice the amount of light come from? It took a while, but then it started to kind of gel in our minds. We went back to electrochemistry. And remember, the electrochemistry we can understand in terms of the fact that we have a donor and acceptor. They're acting independently. Right? I oxidize the donor and I reduce the acceptor. It's kind of independent of the molecule. But that's basically what you do in a device. You inject the electron onto the acceptor and you inject the hole onto the donor. So we thought, maybe when we excite this molecule, or create the excitation on the 2K molecule in a device, we directly form the CT state. Whereas when we optically excite it, we're optically exciting the donor first and waiting for the donor to electron transfer slowly to form the CT state. So we assume that, and it really was a Friday afternoon experiment, and this is Fernando's coup de grace, because it's an experiment he tells everybody never to do. He says, never do absorption and emission in very high concentration solutions, because you get self-absorption, you get a mess. But he did it anyway. You did that? No. Tell the truth. You did it in L configuration first and didn't work, but then he did it in front face. Yeah. So we were lucky in chemistry. We had a fluorimeter that has a front face attachment. So instead of exciting the sample and looking at the emission coming out the other side, you look at the emission coming out the front. So you can use a very concentrated solution, but you can see the emission that comes out off the very thin layer at the front of the device, which doesn't suffer self-absorption. We do that. What we found is that when you look very carefully right on the very foot of the absorption of 2K, there's another transition. That transition is effectively blue shifted as you increase the polarity of the solvent. Its extinction coefficient is about 100. It's very weak. It blue shifts with increasing polarity. It's an unmixed n-pi star transition. And that n-pi star transition effectively gives you direct absorption straight into the CT state. So if you excite right down here on the very foot of the absorption band of 2K, you directly form a CT state. You don't go via the excited donor and then electron transfer. And if you do that, and then you do it carefully, you normalize your emission spectrum, you normalize it from the pump wavelength intensity, and you pump sequentially further and further and further down this tail, you find out that the emission that you get when you pump straight into the donor increases by a factor of 2 when you excite right out here in the tail. So when you directly create the CT state, the PLQY doubles, and it goes from 30% to about 65%. 65% being the magic number, which is what you need to say you can get 18% EQE in your device. So in a roundabout way, what we learned was that the donor and acceptor are almost completely decoupled, but not quite. There is a little bit of coupling, and you can see it goes via the n-pi star transition, and you can directly excite the CT state. It's very weak, but you can do it. When you avoid creating the CT state via the donor, then you get double the quantum yield. So all it's telling you is in the donor state, there's a non-radiative pathway which is in competition with the electron transfer. And not all the excited states you create form a CT. Okay? But what it does tell you is in the device, then it looks like in the device you directly create a CT state. You don't get recombination that forms an excited donor and then that electron transfer to form a CT state. You form that CT state directly in the device. So that's quite important for trying to understand how these TADF systems work in devices. Right. So, let's have a play around what we did next to try and understand things to get into devices. All right. So first off, Tom talked about this yesterday. This was the work when we tried to be clever and rigidly pin the donor acceptor perpendicular by hanging bulky side groups off the donor. When we do that, we certainly pin the thing perpendicular and we stop it moving. And when we stop the donor acceptor rocking and you look at the NMR, you can see at room temperature you lose all the structure in your NMR. And you can only get the structure back in your NMR when you heat it up to about 370 Kelvin. That's basically at room temperature, it's hardly moving. So it's rocking very slowly, which means on the NMR time scale, you can resolve this. You resolve the rocking motion, and it just smears out the NMR. So you've really slowed this rocking right down. And it's only when you really heat it up that the thing is rocking fast enough that it's rocking faster than the time resolution of the NMR, and what you see is that and that. That's where you get the two peaks from. Right? So we thought, well, great, we've made brick dust, and it's the brick dust that we want. The only problem is the brick dust doesn't give you TADF. Because you kill that rocking motion, right, there is no delay component. So the gaps in these spectra here from the CCD camera, that's when the signal has dropped below the signal to noise of the camera. So the camera is integrating a signal over a period of time. And if the signal's so weak in that time period when you integrate, all you see is the noise. You have to integrate for longer to get enough counts to come above the noise floor. So that's why there are gaps here. And then the signal doesn't magically appear, it just means that we're integrating longer to see the signal. But basically, there's no delayed component at all in toluene. There might be a hint of a delayed component in Xeonex. What there is, and what Fernando I think is going to talk a bit more about, is lots and lots of phosphorescence and room temperature phosphorescence. So if we prevent the TADF mechanism harvesting the triplets, we still have lots of triplets. And if we're not harvesting by TADF, you can see them much more easily because you see them as phosphorescence. Okay? So the key thing about this was if you stop the donor and acceptor rocking, you kill the TADF mechanism. It could be a few ways around that you do that, right? So, well, we still haven't said which singlet and which triplet are involved in TADF. Just keep saying singlet and triplet. What's the actual character of the singlet and triplet? So we made this phenoxazine material with a slightly altered acceptor. And yeah, it gives you interesting photophysics. You can see here that this one gives you a much stronger absorption band due to the donor acceptor being connected in the molecule. So that's the donor and acceptor absorption. This is the absorption of the molecule. Right? And you see a brand new absorption band in this case. Right? That redshifts with polarity. So this has got pi star character in this particular molecule. Some of them have n pi star, some of them have pi star. Right? In the absorption. In the emission, then you can see that you get a nice CT band, and the CT band has strong solvatochromism. It behaves itself very nicely like the 2K molecule. So you do the basic characterization. In MCH, so in non-polar, you can actually see that the TADF component is pretty weak. As soon as you cool this thing down, you lose the delayed fluorescence component. Right? So the gap between the singlet and triplet, which is giving you TADF, is obviously quite large in this molecule. So in non-polar, in MCH, right, you can see that this is your initial time decay of the emission. And now you can see the relaxation of the CT state. And by a microsecond, all that's left is just phosphorescence. Right? Because there's very, very little TADF in that molecule. Because the gap between the lowest energy triplet state and the CT state is 160 millielectron volts. Put that into toluene. So this is why I exclaimed yesterday. Right? So I've gone from MCH to toluene. And 95% of the audience would go, what's the difference? Toluene is polar. Right? Only just. However, it has a huge effect on this molecule. Because now you can see, right, the delayed fluorescence component is incredibly strong up here. Right? And in fact, this molecule is great because you get an isoemissive point between the prompt CT and the delayed CT, and you get another isoemissive point when you go over from delayed fluorescence to phosphorescence. And if you look carefully, you can see that here the delayed component gets more intense as you increase the temperature, and the phosphorescence gets less intense as you increase the temperature. So more TADF, less phosphorescence, more triplet harvesting. Okay? You look at the spectrum. Now the spectrum, you get much less shift. And over the whole time period down here, it's basically the same emission, pure CT. It looks like a lovely TADF material. You measure the gap, and the gap is now minus 70 millielectron volts. So now the triplet state is higher energy than the CT state. But I've gone from 160 millielectron volts to 70 millielectron volts. and I get much better TADF. And you can look at the oxygen, or you can do the oxygen measurement. You can look at the ratio of the prompt emission to the delayed emission, and you get a factor of about 5. But it's still a good TADF material. The rate of reverse intersystem crossing is up to 10 to the 6th per second. But all I've done is gone from MCH to toluene. So what have I done? I've shifted the CT band down by, I don't know how much it is, by 230 millielectron volts. Because the CT state is highly dependent on the medium, on the polarity. The triplet state didn't move. The triplet state didn't care about polarity. It stayed the same. So all I did was push the CT state very much closer to the local triplet state. And by doing that, the TADF goes up enormously. And it didn't matter if the CT state is above the local triplet or it's below the local triplet. As long as it's close to the local triplet, TADF switches on. So this is how we knew that the actual states involved in TADF were definitely the CT singlet and definitely the local triplet, which was very close in energy to the CT state. What I haven't said anything about is the CT triplet state. Right? Now, if the CT triplet state is the same energy as a CT singlet state, I'd never see it. I'd never be able to tell the difference between emission from CT singlet and CT triplet. And if we assume for the moment that because we've got perfect orthogonality, then the exchange energy between the CT singlet and the CT triplet is going to be negligible, at which point Crystal goes, yep, they're miles apart, they have exactly the same energy. So what we have is the CT singlet and CT triplet right on top of each other, very close to the local triplet. And at which point we screamed, Tom, what are we doing? And Tom said, oh, wait a minute, yeah. We found the old papers by Lim et al., who'd worked on CT states, and back in the 70s he said that you can't get spin-orbit coupling between CT singlet and CT triplet, just because, as we heard yesterday, they don't couple. The only way that he thought you got intersystem crossing in a CT state was it was borrowing something from a local triplet. So if that's what switches on intersystem crossing, that's what also will switch on reverse intersystem crossing. So that's how we came up when we knew that we needed this mechanism to couple a local state to the CT states. The CT states are really close in energy. And I've got it on a slide somewhere. The best measurement we have of the energy difference between the CT singlet and the CT triplet is 2 micro electron volts. That's from time-resolved EPR measurements. They are really close together. Okay? So it's CT singlet, CT triplet. And that's where the theory comes in to put the two together to understand how you get that mediator state, which is the local triplet, to do the spin-orbit coupling for you. And this is why it doesn't matter if the local triplet is above or below. So it doesn't matter if the population of triplets is sitting in the local triplet state or it's sitting in the CT triplet state. Because it doesn't matter, because the two of them couple and form this thermal equilibrium, and the population is then mixed, and it's a mixed CT triplet, local triplet, and that's what couples back. So as Tom says, it should be absolutely independent of the ordering, the relative ordering of the energy levels, as long as they couple. It's the coupling strength which does everything. Chemik, is it coffee time? Hey?
Yeah, we have first lecture should finish at 9:30.
Right.
Slightly over.
Okay.
The second one at 10:15. We've got 30 minutes of discussion time. And then
Right.